All right. So it's chapter 24. Like I said, we'll do this today. We'll do 25 tomorrow, and then get ready for the final and all that. Most of these are just vocabulary, to be honest. Some of them we've even seen before, like this first one, the electromagnetic spectrum. So this is, like I said, just a way of organizing different types of electromagnetic radiation by their wavelength. So the wavelength is just like the name says, it's how long, the length of the wave. And you can count the wave at the peak of each wave. So like the top one, the gamma rays, at the top of each wave, you can count the distance between those. That's the wavelength. So those are really close together. So because they're really close together and they have a very short wavelength, they have a high frequency. So that means, you know, if there's a point right here, as those waves pass by, a lot of those waves pass by really quickly because they're so close together. It's kind of like, you know, if you're running with like really short steps compared to really long steps. So the more, the higher the frequency, the more energy there is. The more energy there is, the more dangerous it is. So gamma rays, not good things to be around. Like you don't want to be around gamma rays. I mean, those things, they'll kill you. And if they don't kill you, you know, within a couple of days or, you know, a couple of weeks, you know, they have, you know, a higher chance of giving you cancer and things like that. So bad news. You compare that to things like the bottom, you have television and radio waves, which have a very long wavelength. So they have a very low frequency, they have low energy, not real dangerous. And then kind of in the middle, you have visible light. So that's just, I mean, that's what we can see. So like I said, we've seen this before. The sun produces all of these different types of radiation. It produces all types of radiation. But there is, you know, a lot more out there than just what we can see with our eyes. Kind of a big thing. All right, the next one, I think I mentioned it maybe last week, the Doppler effect. This is something that all of us have experienced. We just probably didn't realize it. So with this example, you have the ambulance, the siren is on, it's making noise. But if say you're standing on the street and it's coming down the road, and as it's approaching you, it sounds different than when it passes you and is going away from you. As it's approaching you, that sound and those sound waves are being compressed. So it makes them a higher frequency, so it's a higher pitch. As it's moving away from you, the same sound, but those sound waves are being stretched out. So now it's a lower frequency, so it's a lower pitch. Same thing happens with light when you're talking about in space and galaxies and things moving away. That happens as well. That's the Doppler effect. Because I mean, if the ambulance is just sitting still, siren, it just sounds the same. But you know, the next time you're out somewhere and you hear, you know, an ambulance or a fire truck or something, just kind of pay attention to the sound of it, because it's going to sound different as it's approaching you, as it's, you know, different than when it's going away from you. You can tell your friends, say, oh, that's the Doppler effect. Yeah, I know that one. You'll impress them. The next few slides are different types of telescopes. So the first one is a refracting telescope. So a telescope that uses a lens or multiple lenses to bend and to focus light. Obviously, there are several different types of telescopes, but refracting uses a lens or multiple lenses. And you can get really good results with these. I mean, you can, surprisingly. good results with these. Another type of telescope is a reflecting telescope. So you might be able to guess that it uses a mirror to bend and focus light. And the fact that lenses and mirrors are used in telescopes, I mean, that was one of the big problems early on, you know, in early astronomy and early science, really, was being able to have quality equipment. You know, now if you need to buy a lens that's a certain size and a certain shape, I mean, you get on Amazon and you order it, and it's probably going to be there in a day or two. And it's going to be good. It's going to be really good quality. You know, hundreds of years ago, that wasn't an option. I mean, if you needed a glass lens, somebody had to make it. I mean, by hand. So they had to, you know, make the glass, and then you have to worry about, is the glass clear? Is it, you know, going to have bubbles in it? Is it going to have, you know, impurities? Then it's going to have to be, you know, changed from just a piece of glass into a lens that's, you know, has the right curvature, and is it smooth, and is it polished right? Same thing with the mirror. So, you know, the big advances have been made just because we have, you know, better manufacturing techniques. This next type of telescope doesn't really even look like a telescope. Radio telescope, it looks like a big satellite dish, kind of radio dish, and that's what it is. Because there are so many other different types of radiation besides visible light, that's what these telescopes pick up. These radio telescopes don't so much focus on visible light and how things look to us. They pick up different types of electromagnetic radiation. You know, so they might be interested in, you know, certain parts of the galaxy that are giving off, you know, high levels of X-rays or something like that. And I mean, there are things in the universe that just to look at them wouldn't look exciting. But if you could look at them and see, you know, the different types of radiation that they're giving off, then that's something that's, you know, usable, and that's information that you know, we would like to have. Next one is a Hubble Space Telescope. If you've seen, you know, any kind of space pictures, I mean, like this one in the lower right, like anything like that, almost all of those pictures have come from Hubble. The big advantages of having a telescope like this in space are, first off, the weather doesn't matter. It doesn't matter if it's raining. It doesn't matter if it's cloudy, because it's above the atmosphere, it's in space. So the weather doesn't matter. I mean, it's always clear. And then the other thing is that if you're on Earth and you're using a telescope, when light enters the atmosphere from space, it distorts the light a little bit. So that can interfere with having a really clear, you know, crisp, focused picture. So if you put the telescope above the atmosphere, then you don't have to worry about that. So it's, you know, like I said, it's been up there since 1990. So it's been there about 31 years, and so it's taking some amazing pictures. Yeah. Oh, a new space telescope? Yeah. Yeah, and actually there's one, I can't remember how old it is. There's one that's named after Kepler, and it's looking for like Earth-like planets, basically like planets with liquid water on them. So that's a newer space telescope. I think there might be one or two other ones that are newer, but that's kind of the big one, like the real famous one. A lot of the other ones kind of have specific purposes. That one's kind of a good general one. Or as just kind of a brief overview of the structure of the sun, so kind of how that's set up. One of the big parts of the sun is the photosphere. So photo, the prefix photo just means light. So it's just the surface of the sun. You know, when you look up that, well, don't look at the sun, but I mean, this is the part of the sun that is most visible. Obviously very hot, so don't touch it either, because it's hot. The next part is corona. This kind of outside part of the sun that normally you cannot see. Usually the only time you can see this is during a total eclipse. When the moon blocks out the sun, then you can see the corona around the edge. But typically you can't see it. It's always there, but because the photosphere is so bright, it just kind of overpowers the corona and it just kind of drowns it out to where you can't see it. It's just overpowered. So yeah, that's kind of an interesting part of the sun, like I said, that isn't visible very often. Solar wind. This term is a little deceptive. It's kind of, I mean, it's protons and electrons that are given off by the sun, but it's not like wind here on Earth. It's not like if you're in space, it's going to blow you away, like that sort of thing. It's just different. I mean, it's energy, it's radiation, you know, being you know, given off by the sun, but it's not like wind here on Earth. Sunspots we talked about a little bit before. It's areas on the surface of the sun that are just cooler than other parts. So because they're cooler, the light that they give off is a different wavelength. So it appears darker. Because the more energy, then the higher the wavelength it gives off and the brighter the color. So because it's cooler on those spots, it's giving off a darker color. So sometimes on the surface of the sun, certain features or structures kind of form, like these that are called prominences. And the sun has very, very powerful magnetic fields. And sometimes gases can become trapped in those magnetic fields. And that's what forms these prominences. So these large kind of arches, this whole big thing. Now, one of the kind of crazy things about these prominences is multiple Earths could fit under those prominences. I mean, that's how big these things are. I mean, they're absolutely massive. I mean, you could fit, I mean, like I said, I mean, you could fit many Earths underneath that prominence. Also, the picture on the right, well, it does show a prominence. This is one of the ways that scientists who are studying the sun look at the sun. Because the photosphere is so bright, when they look at the sun, they have, you know, a big dot in the middle of their telescope that blocks out the sun, so then they can see the corona and the outside part of the sun to study that part that they normally couldn't see. And then kind of like a prominence, but a little bit different, are solar flares. So this is when a portion of the sun basically just gives off a bunch of energy into space. Now, sometimes these bursts of energy will hit the Earth. Most of the time they don't, but sometimes they do. It can affect, especially if you're closer to the North Pole or South Pole, it can affect things like GPS satellites, communications, satellites, cell phone service. So it does affect our lives here. They definitely do. In this little animation, it just kind of shows the sun giving off radiation, and then these lines are the magnetic field of the Earth. And it just kind of shows how the magnetic field kind of deflects a lot of that radiation and protects the Earth from the radiation of the sun. Remember that the Earth's outer core, which is liquid metal, it generates and creates that magnetic field, which protects us. So if we didn't have the magnetic field, we wouldn't be here very long. At the little end of the animation, it shows the aurora at the North Pole and the South Pole. So at the poles is where the magnetic field of the Earth begins and ends. And at those places, energy from the sun kind of gets funneled in, and it excites gases that are in the upper atmosphere. And when that happens, they give off light, just like in a fluorescent light bulb. So in the light bulb, there's gas that's trapped in there, and if you put electricity through it, it excites that gas and it gives off light. They said the same thing happens in the upper atmosphere, and depending on what the gas is, then it can give off different colored light. So here's some examples of the auroras, I guess. There's the aurora borealis, which is another name for the northern lights. And then there's also aurora australis, which is the southern lights. Same cause, same phenomena, just one's at the North Pole, one's at the South Pole. And then this is the last slide for today. And this is an important one. So this is how the sun produces energy. They said I would star this or whatever. Nuclear fusion is how the sun produces energy. And when you fuse things, you kind of stick them together. What happens in the sun is there's a lot of hydrogen gas in the sun. Hydrogen has 1 proton. So it takes 2 hydrogens and sticks them together. And then you have something with 2 protons, which is helium. So the same helium that you put in a balloon and it floats, or you inhale it and you talk and your voice is really high pitched. Same thing. So the sun produces energy by nuclear fusion. Now, we have nuclear power plants here on Earth and all that. They don't use nuclear fusion. They use something called fission. So with fusion, you take 2 little things, you stick them together and make something bigger. Fission, you start with something big and you break it down into smaller pieces. The big problem is those smaller pieces are dangerous, and they're dangerous for a long time. So if we could, we would prefer to use fusion, but we don't really have the technology to do that right now. So we use fission sometimes. But I would definitely remember that the sun produces energy by way of nuclear fusion.